Consider the matrix. Oh, this is the 5.2 lesson activities. Consider the matrix A, -4, 2, 3, 1. Find the characteristic equation of A. So the characteristic equation is found by taking the determinant of A minus lambda I and setting it equal to 0. Without the equals 0 part, we call it the characteristic polynomial. When you add equals 0, it's called the characteristic equation. Okay, so A minus lambda I. So A is -4, 2, 3, 1 minus lambda I, that would be lambda 0, 0, lambda. I'm going to take the determinant of all this, and that's going to be the determinant of -4 minus lambda, 2, 3, 1 minus lambda. And the determinant of a 2 by 2 is just AD minus BC. So I've got -4 minus lambda times 1 minus lambda minus 2 times 3. Simplify this a bit. So I get, I'm just going to FOIL here. I get -4 plus 4 lambda minus lambda plus lambda squared minus 6. Combine like terms, and I'm going to write it in descending powers of lambda. So lambda squared plus 3 lambda minus 4 minus 6 is minus 10. And I'm going to set that equal to 0. That is my characteristic equation. To find the eigenvalues of A, we solve the characteristic equation. So this is factorable to lambda plus 5 times lambda minus 2. And so then you set each factor equal to 0. And we get lambda is -5. And lambda is 2. Those are my two eigenvalues, -5 and 2. Okay, we'll just do the same process again. Characteristic equation of A. So I'm going to take the determinant of A minus lambda I. So that's going to be the determinant of 4 minus lambda, 1, 3, 6 minus lambda, which is AD minus BC. And then FOIL it out. So we get 24 minus 4 lambda minus 6 lambda is minus 10 lambda plus lambda squared minus 3. So lambda squared minus 10 lambda plus 21 equals 0. There is my characteristic equation. To find the eigenvalues of A, I just solve the characteristic equation. So this does factor to lambda minus 3 times lambda minus 7. So my eigenvalues are 3 and 7. Okay, we have A here, a 4 by 4 matrix. We're supposed to note that it's triangular, right? We've got this like triangle of zeros, which makes it a triangular matrix. It says find A minus lambda I. So lambda I, in the case of a 4 by 4 matrix, would be lambda 0, 0, 0, 0 lambda 0, 0, 0, 0 lambda 0, and 0, 0, 0 lambda. So I have to do A minus that. So I'm going to get 2 minus lambda, 4, 0, 0, 0, 1 minus lambda, 2, 0, 0, 0, 2 minus lambda, 0, and 0, 0, 0, 3 minus lambda. Now it says, find the factored form of the characteristic equation of A. Pretend you don't know the eigenvalues. Okay, good, because I don't know them. Hint, the determinant of a triangular matrix is equal to the product of its diagonal entries. We learned this back in chapter 3, that if you want to find the determinant of a triangular matrix, you can just multiply its diagonal entries. So this is a triangular matrix. So if I want to find the characteristic equation of A, remember that is the determinant of A minus lambda I set equal to 0. So the determinant of A minus lambda I, because I did lambda A minus lambda I above, the determinant is the product of the diagonal entries. So I'm going to have 2 minus lambda times 1 minus lambda times 2 minus lambda times 3 minus lambda equal to 0. So that is the factored form of my characteristic equation. Find the eigenvalues of A by solving the characteristic equation. So I set each factor equal to 0, and I get lambda equals 2, lambda equals 1, lambda equals 2 again, and lambda equals 3. We don't usually double up when we see an eigenvalue that repeats. Instead, we would write lambda equals 2 multiplicity 2, meaning it's an eigenvalue twice, and then list the other ones. Lambda equals 1 and lambda equals 3. Okay, so it says notice that the eigenvalues of A are the diagonal entries of A. So my eigenvalues of A right here, 2, 1, 2, and 3. Go back up to A, the original A, look at the diagonal entries, 2, 1, 2, and 3. So if you have a triangular matrix, the diagonal entries are the eigenvalues. Okay. That only works, though, because A is triangular. Is A invertible? Yes, because no eigenvalue is 0. Let A be this 3 by 3 matrix, and we're supposed to calculate A minus lambda I. So lambda times the identity for a 3 by 3 would be lambda 0, 0, 0, lambda 0, 0, 0, lambda. So when I subtract them, I'm going to get 5 minus lambda, 4, 2, 4, 5 minus lambda, 2, 2, 2, 2 minus lambda. Now find the determinant of A minus lambda I by following the steps below. So it says knock out the 2 in row 1, column 3. So let's see, row 1, column 3, that's that one. I'm going to knock out that 2 by doing row 1, replacing row 1 with row 1 minus row 2. Oh, I'm sorry, that's not what I'm knocking out. I'm supposed to knock out the 2 in row 1, column 3, this one. Row 1, column 3, by replacing row 1 with row 1 minus row 2. Okay, so row 1 is 5 minus lambda, 4, 2. Row 2 is 4, 5 minus lambda, 2. I'm supposed to subtract these. So 5 minus lambda minus 4 would be 1 minus lambda. 4 minus 5 minus lambda. So 4 minus 5 would be negative 1. And minus a negative lambda is plus lambda. And 2 minus 2 is 0. So my new matrix, I have a new row 1, 1 minus lambda, negative 1 plus lambda, 0. And then row 2 and row 3 don't change. Now, knock out the occupant of row 1, column 2. Row 1, column 2 is right there. By doing replacing column 2 with column 2 plus column 1. So column replacement operations, we've never done these before, but like row operations, they don't change the value of the determinant. You can't use them for row reducing, like if you're trying to solve a system of equations, but if you're trying to find a determinant, you can do a column replacement and it won't change the value. So column 2 plus column 1. So this one plus this one. And that's going to be my new column 2. So column 1 is not changing. Column 2 is the result of adding column 1 and column 2. So 1 minus lambda plus negative 1 plus lambda, those cancel and you get 0. 4 plus 5 minus lambda is 9 minus lambda. 2 plus 2 is 4. And column 3 is not changing. Now, find the determinant of a minus lambda I by a cofactor expansion across row 1 of the matrix from part 2. Okay, so you'll see this row 1, it's got a couple of zeros in it. That makes a cofactor expansion pretty nice. So it's row 1, so I start with not changing the sign. So I'm going to do 1 minus lambda times the determinant of the 2 by 2 matrix that remains when I knock out the row and column that hold 1 minus lambda. So I get 9 minus lambda, 2, 4, 2 minus lambda. And then because of the other two zeros, this would be minus 0 times the determinant of another 2 by 2 plus 0 times the determinant of another 2 by 2, but it's not going to matter because of those zeros. All right. So I'm going to keep working on the first term here. So I've got 1 minus lambda times the determinant of a 2 by 2 is AD minus BC. 9 minus lambda times 2 minus lambda minus 2 times 4. Okay, so it says keep your answer in factored form. So I've got 1 minus lambda times, I'm going to multiply this out. I have 9 times 2 is 18. Minus 9 lambda minus 2 lambda is minus 11 lambda plus lambda squared minus 8. Simplify the bigger parentheses. So I have lambda squared minus 11 lambda. 18 minus 8 is 10, which I believe will factor. So this is going to be 1 minus lambda times lambda minus 10 times lambda minus 1. Solve the characteristic equation, which is the determinant of a minus lambda I equals 0. And I just finished calculating the determinant of a minus lambda I on the previous page. It was 1 minus lambda, lambda minus 10, lambda minus 1 equals 0. So my eigenvalues are lambda equals 1, and that's going to appear twice. So I'm going to write multiplicity 2, and lambda equals 10. Okay, so I've got the eigenvalues, and then for each eigenvalue, I'm supposed to describe the corresponding eigenspace in an appropriate way. Okay, so let's block this off because I have to do it twice. And for each eigenvalue, I have to find x's such that a times x equals lambda x. That's the definition of an eigenvalue, an eigenvector. So let's do this for lambda equals 1 first. Okay, so I'm trying to solve a times x equals 1 times x. I'm going to move everything to the left, so I have ax minus x equals 0, and then factor out an x. So you're going to get a minus I times x equals 0. So a minus the identity times x equals 0. So I'm going to translate this to an augmented matrix. A minus I should remind you what A was. I'll write it over here. A was, from the very beginning of this question, 5, 4, 2, 4, 5, 2, 2, 2, 2. So I have to do that minus the identity. So 4, 4, 2, 4, 4, 2, 2, 2, 1. And I want to augment that with zeros and solve it. So the solution set to this system is all the x's that make this equation true. That's called the eigenspace. So I'm just going to row reduce this on a calculator, and I get 1, 0, 0, 1, 0, 0, 1 half, 0, 0, 0, 0, 0. So that says x1 plus x2 plus 1 half x3 equals 0. x2 and x3 are free variables, so if I solve this for the basic variable, negative x2 minus 1 half x3. Put it in parametric vector form. This is the solution set in parametric vector form. I need a vector for each free variable, and then fill in. So x1 is negative 1 x2 minus 1 half x3. x2 is free, and x3 is free. So this is a way to describe the solution set. All the x's that make ax equals lambda x true, which is called the eigenspace. All right, I'm not going to do the one for lambda equals 10. I will leave that to you. Okay, last problem for these activities. Show that if A and B are similar, then the determinant of A equals the determinant of B. So that is, show that there exists a matrix P such that P inverse AP equals B. If there exists a matrix such that P inverse AP equals B, then the determinant of A equals the determinant of B. Okay, so to translate, what we are given is that A and B are similar. A and B are similar matrices, and that means that B can be written as P inverse AP for some P. And what we need to show is that the determinant of A equals the determinant of B. So hint, start with the given. So P inverse AP equals B, and take the determinant of both sides. So the determinant of P inverse AP equals the determinant of B. And then properties of determinants says that we can do this. Determinant of P inverse times the determinant of A times the determinant of P equals the determinant of B. Okay, determinants are just numbers. So the commutative property does hold here. I can change my order around because the determinant of a matrix is just a number. So matrices themselves are not commutative, but their determinants are. So let's see, I'm going to do the determinant of P times the determinant of P inverse times the determinant of A equals the determinant of B. Then I'm going to use the same property of determinants I used earlier, but in reverse, to write the determinant of P times the determinant of P inverse as the determinant of P times P inverse. Okay, P times P inverse is the identity. So this is the determinant of I times the determinant of A equals the determinant of B, and the determinant of the identity is 1. So we've proven it. 1 times the determinant of A is the determinant of A.